What's up everybody, Adele here. This video is a collection of videos that we have from our course content on Power BI in which you'll learn the ins and outs of using Power BI for DAX, data modeling, data preparation, building dashboards, and a lot more. Of course, this video is only a collection of videos, so if you want to practice on Power BI right in your browser, make sure to check out the link to the courses and the tracks in the description below. And with that, happy learning.
Hi, I'm Yasin, and I'll be one of your instructors for this Introduction to Power BI course. We'll cover the basics of Power BI and have you making reports before you know it. Microsoft Power BI is a tool that helps organize and visualize data from different sources. It lets you connect to data, clean and structure it, create visualizations, and easily share your findings with others. Visually representing data lets people interpret and analyze data faster. For example, it's easier to find the most profitable year in a bar plot than scrolling through a spreadsheet. There are several tools for business intelligence, so why Power BI? According to Gartner, Power BI is the leading BI tool. Over 97% of Fortune 500 companies use Power BI. In total, Power BI has over 6 million customers. With so many companies around the world using Power BI, learning and mastering this BI tool can help you progress in your data-related career. Are you convinced yet? Let's learn more. Power BI Desktop is a key component of Power BI, used for data analysis and report creation on your local computer. It includes features like the query editor and is free to download. We'll be using Power BI Desktop in this course. Paid licenses, such as Power BI Pro, allow publishing to Power BI Service and collaborating with others. Although we're using the free version, everything in this course applies to the paid version as well. Another key component is Power BI Service, the cloud version of Power BI. In order to experience the full benefits of Power BI Service, a license is required. The main purpose of Power BI Service is to share and distribute reports. You will often use Power BI Desktop to create a report and Power BI Service to share that report. Let's quickly review some key areas of the Power BI interface. Once a new Power BI Desktop window is opened, we will see the left side icons for the 4 views: Report, Table, Model, and DAX Query. You can change views by selecting any of the icons. The canvas area in the middle of the report view is where visualizations are created and arranged. In the Filters pane, you can filter data visualizations. In the Visualizations pane, you can add, change, or customize visualizations. Finally, the Data pane shows the available fields. You can drag these fields onto the canvas, the Filters pane, or the Visualizations pane to create or modify visualizations. In this chapter, we'll be using data from a fictional company called Wide World Importers, a wholesale novelty goods importer and distributor operating from San Francisco. Wide World Importers has provided several data files, typical when dealing with real-life data. All sales data is in the fact sales file, also known as a fact table, as they contain events or facts related to company activity. Additional files contain dimension table data, like dim customer, which stores customer contact information. You can create relationships between tables through matching columns, so Power BI knows they are related. Welcome to Power BI Desktop. When you open a new desktop file, you're greeted with the default report view, where reports and visuals are created. The ribbon at the top offers various options. For instance, the Insert ribbon is focused on visuals, while the Modeling ribbon handles data connections. Let's start by connecting some data. Under the Home ribbon, click the Get Data button. Power BI offers several options, but we'll import a CSV for now. Select Text CSV. Next, let's open the fact sales file, which contains sales transactions for AdventureWorks, a fictitious bicycle manufacturer that sells bicycles and accessories. After selecting the file, a preview window appears. We can simply click Load and the data will now be available in Power BI. Once the data is loaded, you'll notice the fields listed in the data pane. Let's switch to the table view to see the raw data more clearly. The fact sales table's values are displayed, and the Table Tools ribbon offers options for interacting with the data. One of Power BI Desktop's strengths is its ability to combine data from multiple sources. Let's add another table from within the table view. We'll use the Get Data button again, but select an Excel file this time. We'll load the DIM products table, which contains details about the product involved in each transaction. In the preview window, choose the correct sheet from the Excel file and click Load. The new table appears in the data pane. Now, let's explore the model view. Here, we can see all the loaded tables. Power BI automatically creates relationships between tables when it detects common fields, such as the product key in both tables. If needed, relationships can be deleted by right-clicking on them. To manually create one, simply drag a field from one table to a matching field in the other table. Let's move to the report view to create some visuals. First, select the sales amount field from the data pane. Power BI automatically generates a bar chart because it recognizes this is a numerical value, adding it to the y-axis in the visualization pane. You can easily resize and move the chart by dragging it around. Let's enhance this visual by adding more data. With the chart selected, expand the DIM products table in the data pane. Drag the category field to the x-axis. Now, the bar chart reflects the sales amount for each category. You can hover over each bar to see the sales figures. Let's add another visual, a card visualization showing the total sales amount. Click a blank spot on the canvas, choose the card option in the visualization pane, and select the sales amount field. The card now displays the total sales amount. The visuals are interactive. If you click the Components bar, the card updates to show the category total. Click on the bar again to reset the view. You can easily switch visualization types. Select the bar chart, then choose another visual type from the pane, such as a tree map, and the chart will change instantly. Finally, you can add new pages using the plus sign at the bottom, or delete them by clicking the X on any page tab. You can also load pre-existing reports by clicking File, then Open, and selecting Browse this device. Let's continue from where we left off. We want to add some more fields to our tree map visual, but let's first change it to a clustered column chart. In this chart, we can add the total product cost to compare it with the total sales amount field. There are now two bars for each category and a legend above that indicates what each color means. Note that the numerical field has automatically been added under the y-axis section in the visualizations pane. It would be useful to analyze this plot based on sales territory. In the table view, we can see the fact sales table has a field called Sales Territory Key. We have a dimension table available to us called DIM Sales Territory that holds more information on this key. Let's access this CSV file and load it. In the table view, we see that it's what we're looking for because it contains information about the territories that AdventureWorks serves, allowing us to identify where each sale originated. In the model view, we see that Power BI has already recognized a relationship between the fact sales table and the DIM sales territory table, based on the column Sales Territory Key, so there's nothing to do here. Back in the report view, we will add a slicer to the canvas by selecting the slicer icon. A slicer allows viewers to filter the visuals based on a field of their choice. we will filter our visuals by the country field. And from the list, we will choose Canada. By clicking on the columns in the column chart, we can filter further on category. Now, let's try out a new visualization, the table. We have to select a blank spot so as not to modify any existing visualizations. Click on the table icon in the visualization pane and let's select a number of fields to go into it, such as group, product, color, list price, and standard cost. Let's rearrange things to look a bit neater. Our selections in the chart and slicer affect the table as well. We can add a title using a text box. We can customize the text and increase the font size so it's clear. Finally, we should rename the page tab so that it matches the title. And now, it's time for you to add to your report.
Nice job so far. Let's move to transforming data. Why do we need to transform data? Well, datasets rarely come in a perfect form and you need to transform the data to fit your needs. Depending on what you want to do, there may be columns you don't need or inconvenient and inconsistent formatting of values. Often there are processing errors that cause extra characters or blank rows. These are just a few examples. This type of transformation is often referred to as cleaning data. Previously, when you loaded data, this preview pop-up screen appeared, and we immediately loaded the data. Now, in the next exercises, we will transform first. Specifically, you will use the Power Query Editor, which is a tool that allows you to edit the data prior to loading it. You can use it to format the dataset and decide what gets loaded. The Power Query loads in another screen shown here and uses a language called M. However, you don't need to know M to use it. Note that because the Power Query Editor opens in a separate window, you'll need to close it to go back to your report. An important thing to know about Power Query is that you need to close and apply for any changes to be made to the data in the report.
Let's load another CSV file called dim customers, which contains information about EventureWorks customers who have made purchases. In the past, we've gone straight to load, but in the preview, we can see something weird happening in the first rows. Let's transform the data instead. This is Power Query Editor, which allows us to transform the data before loading. To remove this top row holding unwanted information, we can use the Remove Rows action above. It has several options, but we'll use Remove Top Rows. We enter 1 because we only want to remove the first row from our dataset. Note that the section here, Applied Steps, tracks our changes. I can go to an earlier version to see the deleted row. We can see that Power BI has already automatically applied these 2 steps when loading the data. Looking at our column names, we still need to do some work. Incorrect header names are a common problem, and Power BI has an action called Use First Row as Headers, which is available to help solve this. Again, we see this change in the Applied Steps panel. Looking through the data, there are a couple of columns we could delete, like Valid From and Valid To. We can select them and press Remove Columns. Most importantly, we need to close and apply to save our changes. Now, our changes are being applied. In the model view, we can see that Power BI automatically recognized a relationship with our new table, so there's nothing to do here. Back in the report view, we can pull up the Power Query Editor again by selecting Edit Query from the menu that appears when clicking on the ellipsis next to a table. We can edit our changes. For example, we can undo the removed columns if we change our minds. Again, we close and apply. Let's add a new page at the bottom. Here, let's quickly visualize the color of the products sold and their unit price using a clustered bar chart. Is it possible to tell if there is a relationship between color and price? We can't tell right now because our graph shows the sum of all the unit prices, which will take into account the number of each item sold. This is because Power BI automatically sums numerical fields in a visualization. If we go to unit price, we can change the aggregation from sum to average. In general, there are many other possibilities. We could take the minimum, maximum, count, or any other aggregation function listed here. On average, red products cost the most, but we would have to do some more digging to be sure. It's time for you to try out Power Query Editor. Let's continue cleaning our data. In the data view, we can load the Power Query Editor by clicking Transform Data. Let's look at dim products. If we select a column, there are a couple of things to note. For example, for standard cost, we see that the data type is a decimal number. This makes sense here, but note there are other options, like percentages, or for something like color, we have text. We see there's something wrong with the subcategory column. It has a question mark in front of every value, which is probably a processing error. To fix it, we select the column and then use Replace Values to search for all the question marks and replace them with blanks. Let's close and apply to save our changes. We have seen how to set data types for columns, but what about formatting? For example, say we want to have the standard cost always appear as a currency in the visual we create. We can do that in the data view. First, we select the standard cost column and Column Tools appears above. We can change the format from general to currency. We can also change the number of decimal places by adjusting this section. Let's set it to 0. Another useful feature is the summarization field here. You can change the default summarization type for a specific column from here, so that you don't need to keep changing it each time. To see if our changes have been implemented, let's add a card visual to the report and display the standard cost. Great! We see the average value with currency format applied and 0 decimal places. Let's look at geographic data. In the dim customers table, we have several columns representing geographic areas. We can put these in a data category, like city or country. Data categories allow us to specify what type of geographic data the column contains. Using these categories, we can create map visualizations. Note that globe icons have shown up next to the city and country region fields, indicating that they are recognized as geographic values by Power BI. Let's add a map visual by clicking on the corresponding icon. We can then use the country region as the location and count the number of orders placed by country using the sales order line key as the bubble size. Now, the circles on the map are proportional to the quantity of orders placed in each location. Time for you to give it a go.
Hi there! Great job on completing the first 2 chapters. I'm Sarah, and I will be your instructor for this chapter, where I will focus more on visualizing data with Power BI. Power BI provides a number of different visualization types that you can use in reports. So far, we have only looked at a few of them. Let's find out what else is possible in Power BI. In this course, we'll only focus on what type of visualizations you can make with Power BI. Obviously, it's also extremely important to know when to use which type. You can learn all about this in DataCamp's Understanding Data Visualization course. Bar and column charts help you look at a specific value across different categories. So, what is the difference between the two? The answer lies in the representation. If the rectangles are placed horizontally, then the visualization is a bar chart. If the rectangles are placed vertically, then the visualization is a column chart. There are a number of different column and bar chart types available in Power BI. A stacked bar or column chart includes multiple elements in one bar. It shows the different series as a part of the same single column bar, where the entire bar is the total. A clustered bar or column chart shows multiple bars to represent values, but this time they are located next to each other instead of being stacked. A 100% stacked bar or column chart shows the relative percentage of multiple data series in stacked bars, where the total of each stacked bar always equals 100%. A combo chart combines a column chart and a line chart. Line charts show multiple lines in one chart. They emphasize the overall shape of an entire series of values, usually over time. Area charts are based on line charts with the area between the axis and the line filled in. Pie charts show the relationship of parts to a whole. Donut charts are similar to pie charts. They show the relationship of parts to a whole. Tree maps are yet another way of showing the relationship of parts to a whole. They are charts of colored rectangles with size representing the proportional values. The next set of visuals are designed to show one or two values and are used for showing the overall level of performance. Cards show one value, whereas multi-row cards can display multiple. Gauge and KPIs are designed to show actual data compared to budgeted data. Both of these visualizations show detailed text data in a tabular format. A table is a grid that contains related data in a logical series of rows and columns. It may also contain headers and a row at the bottom for totals. A matrix is similar to a table in that it is made up of rows and columns. However, a matrix can be collapsed and expanded by rows and/or columns. In the example, you can see that we expanded the data to focus on region for mobile loads of page 1. All the charts we just discussed can be edited using the options included in the paintbrush. We'll take a closer look at how to do that in the next video. This chapter uses data from the Contoso data warehouse. Contoso is a fictional online retail company that is working on trying to meet sales goals. Just like in the previous chapter, this dataset is made up of multiple files. This time around, the fact table is called Fact Strategy Plan, and it contains data on the sales transactions of the company. The dimension tables hold more information about these transactions. We'll work with the account, date, entity, product category, and scenario dimension tables. In this demo, we'll see how to change and edit different Power BI visualizations. Let's start by taking a look at the data. Notice that the Contoso data warehouse tables have been added to the report. These tables contain the fact table, Fact Strategy Plan, which contains the actual, budgeted, and forecasted transactions. There are also 4-dimensional tables: DIM account, DIM date, DIM product category, and DIM scenario, with more information on the transactions. All of the relationships have been created, so there is no need to modify the data model. As you can see, there are a number of different visualizations used in this Power BI report. On the top left, we have a card with the total amount. Next to that, a donut chart that shows the amount by account type. We can hover on a visualization to show more detail. On the right of the donut chart, the legend is displayed. On the top right, we can see a 100% stacked bar chart. Each account type category makes up 100% and each product category is expressed as a percentage of the total. Below that, we have an area chart. It shows the actual, budgeted, and forecasted amounts for 3 years. Next to it, we can find a slicer that can be used to filter the data on year. When we select 1 year, the graph changes to dots, which isn't ideal. Let's fix that later. To clear selections, you can click on the eraser icon on the top right corner of your visual. Finally, at the bottom of the report, a matrix has been added. It shows a summarized version of the data. We can change any of the visuals on the page by clicking on the visual to select it and then clicking on another visualization icon. When you select the visual, you can see what type it is by looking at the little gray box in the visualizations pane. In this case, an area chart. We saw that selecting 1 year makes the chart look odd, as you only see a dot. Let's change the visual to a clustered bar chart. We can now see the same data, but represented in a different format, and now it looks better when only a single year is selected. If we want to change any of the properties of the chart, such as changing the font size, we can do that by clicking on the Formatting icon, which looks like a paintbrush in the Visualizations pane. Let's edit the slicer. Under Slicer Settings, then Selection, add a Select All option and turn off the slicer header. Here, we can also change the size of the values in the year slicer to a larger font. This can be edited under Values. We'll resize it from 10 to 12. Let's change and format another visual. This time, we are going to change the matrix to a table to show more detail. Let's edit some of the properties as well. We'll make the columns wider by hovering over the boundary and dragging it to the right. There we go. See how easy it was to make edits to visuals? Your turn. In this demo, we'll see how to sort data in Power BI and look at some more formatting options. Let's start by sorting the years in the slicer in descending instead of ascending order. We can do this by clicking on the 3 dots in the top right corner and changing the sort from descending to ascending. We can do the same thing for the clustered bar chart. Click on the 3 dots and then go to Sort Axis. Currently, the data is sorted by amount, which is why November is first. Let's change that to sort by month name. Uh-oh, looks like September is the first month now. If we order in ascending order, April is first. It seems like the months are sorted in alphabetical order. This is not what we want. To sort the data in the correct way, from January to December, we need to modify the data. To do this, we'll go to the Table view. Here we'll select the Dim Date table. Now, what we want to do is modify a property of the data so it will always sort the way we want. The field that was used in the clustered bar chart is month name. Let's select that column. When doing that, the contextual menu at the top of the screen changes and there is an icon that says Sort by Column. In our case, we want to sort by the month number instead of in alphabetical order. We need to click on Sort by Column and then make sure to sort the month name column by month number. Let's do the same for short month, so that if we choose either of these columns, the data is ordered in the correct way. Click on Sort by Column and sort by month number. Let's go back to the report. As you can see, the visualization now orders the data the way we want it to, from January to December. Now, let's apply some additional formatting to our report to make it look nice. First, we are going to resize the tree map. Click on the paintbrush to navigate to the Formatting pane, and under General, then Properties, change the height to something smaller, let's say 250. This way, the tree map doesn't overlap with the visual below. We could use this functionality to make visuals to be the exact same height or width. This will help make our report look better. Let's also change the formatting on the slicer. Instead of showing a list of years, we want to display a drop-down menu. To do this, we go to the Formatting pane and find the Slicer Settings section under Visual. In the Options section, we can select the style of slicer we want, such as a drop-down. This limits the space the slicer takes up in our report. As a final edit, we are going to change the theme of the report. To do this, we'll navigate to View menu on top and click on this little arrow in the Themes pane. This will show us all the available options. Let's choose the Innovate theme. That looks good, right? Alright, you now know how to sort data and edit your report. Time for exercises. Welcome back. You don't always want to show all the data in your Power BI report. Sometimes it can be useful to reveal additional detail by drilling down or show only a subset of the data by filtering. Let's start with drilling down. Drilling down allows a single visual to show data at a high level and then gives the user the option to look at the data at a more detailed level. This action is made possible by creating hierarchies. An example of a hierarchy might be year, quarter, month, day, or company, region, country, division, and unit. Once a hierarchy is created, you can navigate up and down to lower levels. There are different ways to do this. Power BI has a set of drill controls that allow you to look at data in different ways. In this example, we're using a column chart that has a hierarchy made up of year, quarter, and month. The chart, before drilling, looks at the sales amount by year. Selecting the double arrows icon drills down on all fields at once. It takes you to the next level in the hierarchy. If you're looking at the year level, you can drill down to quarter level for all years, and then month level for all years. Note that the amounts you see here are the sales amounts by month for all years. So, the January amount is the total of January 2017, 2018, and 2019 added up. The next control, Expand, adds an additional hierarchy level to the current view. So, if you're looking at the year level, you can expand and add the quarter and month detail to your column chart. Each step in the path shows you the same information and adds on one level. This time, we see the sales amounts for January each year are shown as separate columns. Next, we'll look at filtering. Often, you don't want to look at all of your data at once, but rather display data based on some selected criteria. Using filters, you can filter out unnecessary information. For example, you can filter a report so that all of the data is for 1 year or one customer. You can also change a filter so that it shows a smaller set of data, like the last 2 years or the top 5 regions in terms of sales. You can apply filters on different levels in Power BI. Visual level filters are applied directly on individual visuals. Page level filters apply certain filters on a selected page within a report. Report level filters are filters that you use to apply a filter on the entire report. It's possible that you don't want the end user of your report to be able to change the filters. For example, if you have a visualization focusing on computer sales, it wouldn't make sense for the user to be able to change the filters so a different product is displayed. You can do this in Power BI by changing the interactions. Changing interactions means the visual will not change when another field is selected. We'll take a look at how to do this in the upcoming videos. In this demo, we'll learn how to look at the underlying data of a visual, how to export data, and how to create hierarchies. Let's start by looking at the underlying data. Sometimes you'll want to look at the data that is used to generate a visualization. Think of, for example, users that work a lot with Excel. They are used to always seeing the data. We can do this by clicking the 3 dots on the visual of interest and then selecting Show as Table. By doing this, we can see not only the visual, but also the data that is used to generate it. From here, we also have the ability to export the data to a CSV file, for example. CSV means comma-separated values. It's a text file where values are separated by commas. Let's go back to the report. Note that we can also skip showing the table and export the data directly. Next, we'll learn how to create hierarchies. In the column chart, we are looking at the month data, but let's say we want a more detailed perspective on the date. It would be really nice to be able to drill down on the date in an organized manner. For example, in the year, quarter, month, day format, which is commonly used. We can achieve this by creating a hierarchy. To do this, we'll go to the table view. So, we want a hierarchy that starts out with the year, goes to the quarter, let's use the short name, then goes on to the month, we'll use the full name, and day. Click on the 3 dots next to the year column and select Create Hierarchy. When we do that, a hierarchy is automatically created. We are going to rename the hierarchy by double-clicking on the hierarchy name and changing it to Date Rolled Up. Then we'll add the quarter and month name columns. We do that by right-clicking on the column names and then adding them to the Date Rolled Up hierarchy. Next, we'll also add Date Key, which will allow us to drill down to the day level. By the way, you can switch the order of the levels in the hierarchy by going to Model View, selecting the hierarchy that has been created, and in the Properties pane, you can change the order of the columns. Let's go back to the report view. Note that we could have also created the hierarchy from the report view on the right here. Time to start using the new hierarchy. Select the column chart and change the axis field from short month to the new hierarchy. Don't forget to delete short month. When we do that, new controls appear at the top of the visual, which are the drill down controls. Clicking the down arrow turns on the drill down. After doing that, it turns black, meaning it is enabled. If you don't turn on drill down, selecting a visual element won't drill down. Instead, it will cross-filter the other charts on the report page. As we've covered earlier, the double arrow will get us down another level for all years, and the double arrow with the line combines information from the current and next level. Feel free to play with this on your own to get a feel for how drilling works. Let's drill down one field at a time. To do this, we'll select the bar corresponding to the year 2018 to see the amount by quarter. If we now click one of the quarters, we only see the months in that quarter of 2018. Hierarchies are a really cool way of organizing your data. Let's see if you can create them yourself. In this demo, we'll learn how to work with filters. We've added a new dimension table called dim entity to the data. This table contains information on sales locations. As you can see, the entity key field can be found in the fact strategy table as well, and that is what they are joined by. Let's look at the report. This visual is about the sales amount by location, the location being a value in the dim entity table. Wow, looks like there are a ton of locations. We want to show only the top 10. To do this, we'll click on the visual to select it. Notice that when we do this, an option to filter on the visual pops up on the filter pane, here on the right. Click on Entity Name, and under here, where it says Basic Filtering, select Top N. So, that is going to give us the top N number of entities, meaning locations, and we want 10. The value we want to select the top locations on should be the amount. Click Apply Filter. That looks better, right? Let's sort the columns by the amount, in descending order, so it's easy to see the top 10 locations. Seems like Contoso Catalog is the top one. Finally, we'll change the visual to a clustered bar chart to mix the visuals up a bit. There we go. Next, we want to filter all pages to only show actual sales amounts. To do that, we need to look at how the data is reported. Let's go to the table view and look at the values in the fact strategy table. We can see that the values have a scenario listed. If we go to dim scenario, we can see that the scenario tells us whether the amount is actual, budgeted, or forecasted. We're only interested in the actual values in this report, so let's add scenario name to the filter pane. We want to filter on all pages, so let's drag scenario name to filters on all pages. There are 3 options. Only select actual. Now, every single amount value is just the actual amount. That is going to impact every page. Note that it's also possible to filter on a single page. Notice that every time we click on a product category, the actual amount changes. But we don't want it to change. We want it to always be the same. Let's go into the Format tab on top and edit the interactions. When we do that, you'll notice filter and no symbols popping up on the visualizations. Let's select the monthly amount visualization. Since this is the one highlighted, this is the context the filtering is going to happen in. This means that by editing the interactions, we can change how the selected visualization, the monthly amount chart, interacts with the other visualizations on the report page. Let's turn off the interaction. Now, the actual amount will not be filtered based on what is selected in the monthly amount visual. Let's do the same thing for year. Note that you might have to move some visuals around to see the interaction icons. Let's look at the result. Turn off the Edit Interactions functionality in the top left corner. You can see that the interactions are disabled. If you select a product category, or filter on year, the actual amount card in the top left corner doesn't change. Over to you.
Hi, I'm Jess. I will be your instructor for this introductory course on DAX. We'll cover the basics of DAX and have you writing DAX calculations before you know it. DAX stands for Data Analysis Expressions. It is a formula language used in Power BI that provides the ability to create columns, tables, and measures. If you've ever used Excel formulas and functions, good news! DAX is to Power BI what formulas are to Excel. For example, the sum function is the same in Excel as it is in DAX. DAX is more than just Power BI. It is used in other Microsoft tools, including Analysis Services and Power Pivot. Functions are predefined formulas that perform calculations on specific values, called arguments, in a particular order. Each function has a specific syntax indicating the order of arguments to be expected. DAX has over 200 different functions that fall into several categories, including aggregation, date and time, logical, text, and many more. You can find a full list of all functions and their syntax in Microsoft's documentation linked here. Let's take a look at two examples, starting with the sum function. The sum function takes a column and adds up all the numbers. It has one argument. In the example, we are summing the sales column. The left function takes two arguments, a string and an integer. It returns a specified number of characters from the start of the string. In our example, we input datacamp and specify 4 characters, which returns data. Calculated columns can be very useful as they enable us to expand our existing dataset without editing the source data. Calculated columns evaluates at a row level and therefore adds a new column to an existing table. Any column that is created is calculated at data load or when the data is refreshed. Let's say we are trying to calculate price with tax. For this, we start by defining the column name, followed by an equals, and proceed to write our formula. In this case, price plus brackets price times tax, close brackets. In the table below, we can see this implemented in a real-world scenario. Calculated measures work a bit different. Measures enable you to create complex calculations that can be used on your data. Where columns evaluate for each row, measures aggregate multiple rows and adds a new field that can be added to a visualization. The measure itself is calculated at query time rather than when the data is loaded, therefore gets updated as you interact and filter the data. This means it is more efficient because the calculation isn't run every time a table is accessed, instead only when it is being used. Measures can be created in two ways, by writing a DAX formula or by using Power BI's Quick Measure. We will get into quick measures later on in the course. Let's go back to our previous example and calculate the total price with tax that uses the sum function to calculate the sum of all prices with tax together. We can now add this measure to a card in a Power BI report to discover the total price with tax is $185. To summarize, calculated columns evaluate for each row. It adds a new column to an existing table and is calculated at data load or when the data is refreshed. Whereas measures aggregate multiple rows, results in another field that can be added to your visualization and is calculated at query time as you interact and filter. In later chapters, we will dive into calculated tables. In our exercises, we'll be working with data from the fictional bike company AdventureWorks that sells bikes and bike parts globally. We will have a table called Sales, which contains information about every order item purchased. Now it's time to learn how to create calculated columns and measures in Power BI. We'll be using a single table that contains transactional information about commodities traded every day from January 2000 to March 2022. You can see all available columns by clicking on the drop-down next to the table on the Fields pane. Let's start by renaming the report page from Page 1 to Commodities. We will start with creating our first calculated column. This can be created from inside the report or data view by selecting our table and clicking New Column. Our table Commodities contains an open price and a close price, but we do not currently see the trading difference for each day on each commodity. We create a new column called Trading Change, followed by an equal sign. As we start to type close, Power BI's IntelliSense leaps into action and shows us a list of all columns and functions that match our text. From here, we can select close, followed by a subtraction sign, then open. Now we can commit this new column by clicking the check mark or pressing enter. Our new column looks great. Now it's time to create our first measure. As our reports develop, we will start to create a multitude of measures, which can easily get lost in our data model. It's best practice to create a calculations table in our model that acts as a folder for all our measures. It doesn't contain any actual data, but rather a placeholder for all our measures. The naming convention will always start with an underscore so that it appears at the top of the Fields pane. As you can see, this has already been created for you and called Calculations. When you create a new measure, make sure that you have selected this table. We will create a new measure called Max Close Price, which computes the highest closing price. For this measure, we will now use the max function, which takes a column name. In this case, our close column. We can now close this function with a parentheses and commit. We can now see our new measure in our Fields pane under the Calculations table. Now that we have our measure created, let's visualize it. Let's select a line chart from the Visualizations pane and pull in our max close price and date. We can see that the max close price for commodities trended upwards till 2011, before taking a dip and then slowly improving up until 2022. Another great feature to get familiar with in Power BI is the drill down function on charts. It enables you to go from a high-level view to a more granular level when a hierarchy in the data exists. For example, our date uses Power BI's built-in date hierarchy. We can use the drill feature to select 2014 and drill into the quarters for that year. You can keep drilling till you get to the lowest level, in this case, day. Equally, we can use the drill up feature to move back up the hierarchy. Alternatively, you can drill down to the second level of the hierarchy, not just the selected year, but all years to see how it changes at a quarter level. The selective drill down doesn't give you this option. To achieve this, you can use the fork-like button. We can now see a new view for max close price. Now it's your turn. Let's use the knowledge you've learned in this screencast and apply it. Welcome back. In this chapter, we'll take a closer look at context in Power BI. We'll also dive deeper into DAX formulas and understand the use of variables and the calculate function. Context is an important concept to understand in DAX. It enables dynamic analysis where the results of a formula change to reflect the selected data. There are three types of context: row, filter, and query. In this chapter, we will cover row and filter context, which are key to becoming a DAX master. Query context falls outside of the scope of this course. You can learn more about query context in future DAX courses. Row context can be thought of as the current row. A calculated column is an example of where row context applies. In a calculated column, the context includes the values from all columns within the current row. In the table below, we have a calculated column, price with tax, which contains a formula that does a calculation on the price and tax column. As you can see, the calculation is happening row by row, a perfect example of row context in action. Row context can also be used in measures, however, only when using iterator functions. An iterator function loops through every row in a table and runs the formula for each row. An iterator function can be identified by an X at the end of a function name. For example, SUMX takes two arguments: the table that needs to be iterated over and the calculation that needs to happen, similar to what we'd use in a calculated column. For example, if we wanted to get the output of our price with tax column without ever creating a calculated column, we could use SUMX to iterate over each row and perform the calculation. This would give us a total value of $70. Filter context is a set of filters that have been applied before the calculation is carried out. They can be applied in several ways, including attributes in a row or column, via a slider, through the filter pane, or in a calculated measure. In this example, we have a table of data and we'd like to apply a filter of blue. In order for Power BI to return a value for the color blue, it will go to the base table and apply a filter where color is equal to blue. This is filter context. It is applying the filter context on each quantity returned by color. Starting from our original table, we can extend this further by creating a matrix of color versus product category. This changes the filter context again, because for each data point that is returned, Power BI is applying filter context. For blue socks, a filter is being applied for color being equal to blue and product category being equal to socks. Now that you've understood filter context, let's introduce you to the calculate function. Calculate allows you to evaluate an expression with one or more filter context. The calculate function takes two arguments. One argument is required and the other argument is optional. The first argument contains the expression to be evaluated. This must return a single value. The second argument for adding filters is optional, but you need to ensure that the filters evaluate as a table and do not clash with one another. For example, sales city is equal to London and sales country is not equal to United Kingdom. The filters inside the calculation will always override any filters from a visualization. You can see an example of calculate in action. Here we are calculating total sales in EMEA region. Now that you've seen the difference between row and filter context, in the demo we'll continue with our commodity dataset. We'll be diving deeper into DAX measures, applying iterators, and learning how to use variables in a calculate function. In the last chapter, we created a calculate column to work out the difference between the opening and closing price. Now we'll create a measure that uses an iterator function to do the same calculation. First, we'll start by creating a new measure called average trade difference and start by typing average, which will use Power BI's IntelliSense to show all the matching functions. We'll select average x from the drop-down list. The average x function takes two arguments: the table where the aggregation will be applied, in this case commodities. The second argument will be the calculation we are looking to perform on each row. In this case, it will be close subtracted by open. We can now commit this measure by pressing enter. Let's visualize this on a card. We can now see the average daily trade difference of 3.58 across all commodities. Great! Now we've created our first measure using an iterator function. Next, we're going to learn how to use the calculate function. These are one of the most used functions in DAX due to its ability to modify and have priority over the filter context. We'll create a new measure called gold volume 21. For this measure, we want to get the sum of all gold trades that occurred in 2021. In our calculate function, our first argument will be the sum of volume. Now that we've added our expression to be calculated, we can now add the filters we want to apply by using the filter function. The filter function takes a table to be filtered and the specific filter to be applied. Our first filter will be on the table commodities, where symbol is equal to gold. Next, we'll filter the same table again, but this time filtering for the year 2021. For this, we will be using the year function, which we will cover in the next chapter. Great job! Now we can visualize this new measure on a card. We can see the total gold volume for 2021 is 308,000. The final concept we'll be covering is a new topic we haven't covered yet called variables. Variables are very useful when writing DAX calculations. As you write more DAX formulas, you'll see that they can get very complex very quickly. Variables help simplify your code as well as increase readability and performance. Variables can contain static values or snippets of code that may be reusable in your query. To get familiar with variables, we can look at using variables in conjunction with calculate. We've created the measure gold volume 21, but how about if we'd like to see the percentage growth in volume versus 2020? A measure has been created called no variable. Let's take a peek. This shows us a DAX formula that does not utilize variables. If you look closely, you can see that the calculate function is being used twice. This is inefficient for Power BI as it has to evaluate the same expression twice. Let's copy the formula as we'll be using this in our new measure. Let's create a new measure that uses variables called gold 21 versus 20. First, let's create a variable called gold volume 20. Here we can paste the formula we just copied. Now we have a variable that calculates gold volume for 2020. We'll now declare our return statement that will compute our calculation. We will use the divide function to work out the percentage difference. For the numerator, we'll calculate the difference between 2021 versus 2020. So gold volume 21 minus gold volume 20. Next, we'll set the denominator to be gold volume 20. We can now commit this measure and format it as a percentage and round it to 0. Now we can put this into a card visual and see that there was a massive increase of 480% in trades of gold. We've seen variables, iterators, and calculate in action. Now it's your turn. Let's practice. Welcome back. In this chapter, we will be looking at dates in Power BI. We'll learn about the importance of having a standalone date table, as well as how to use date and time intelligence functions in DAX. We'll finish off this chapter by learning how to create quick measures. Power BI has hundreds of built-in functions available. We'll walk through some example date and time, format, and time intelligence functions using the date 20th September 2020 at 12:52 p.m. as our datetime argument. Using some of the date and time functions, we can pass through our datetime. For the year function, it will return 2020, quarter returns 3, and month returns 9. However, on some occasions, we want dates formatted in ways that the current date and time functions cannot provide. For example, if we want the weekday name of the date, we need to use the format function, where we pass our argument and the desired format expression. In this case, we will type D 4 times. An exhaustive list of all format functions can be found in the DAX documentation. Power BI also has various time intelligence functions available, but we'll look at them later when creating quick measures. Working with dates in your reports is very common. There will always be occasions where we need to evaluate data in a time series to be able to spot trends and patterns. Out of the box, DAX has useful functions and features that support working with dates. It contains over 20 date and time functions and over 30 time intelligence functions, and it is able to generate date hierarchies to drill down on visualizations. Date hierarchies can be very useful, but there are some pitfalls that occur when relying on dates from a transactional table like sales. Time intelligence functions rely on having dates in a table that contains no gaps. For example, if our sales table had no transactions for a particular day, then the function which called it will return the wrong result. This is important to consider because it will not return an error, just the wrong result, making it difficult to troubleshoot. A dedicated date table in your model is highly recommended for accurate reporting, particularly if you'll be using time intelligence functions. There are many benefits for using a dedicated date table. You can filter across multiple date attributes such as month and year. You can create custom calendar views and definitions to match your financial year. Additionally, you can use time intelligence features to select a time horizon, such as last 30 days. You can then apply this to many types of analysis, including revenue by day of week, fiscal, and public holiday performance. Let's learn how to create our date table. In DAX, there are two ways to achieve this. First, we can use the calendar function. It takes two arguments, a start and an end date, and returns a table with a single column containing a list of dates inclusive of the specified dates. In this example, we are creating a date table for dates between 1st of January 2020 to 31st of December 2020. The other function we can use is Calendar Auto. Behind the scenes, it calls the calendar function. Power BI will automatically provide the earliest and latest date in the model as arguments. However, fiscal year end month needs to be specified for the last fiscal month you want to see after the last date. For example, if the last date was 2020-07-27 and we specified 12, we'd see the dates until the end of the year. Similar to previous chapters, we'll be working with the commodity dataset. First, we'll create a calculated date table, learn how to apply functions, and understand how to create our first quick measure. We'll start by creating a new page called Dates. In previous lessons, we covered the importance of a well-formatted date table. So let's create it. Let's navigate to the Modeling tab and select New Table. This will open up a new formula bar, and we'll start by naming our table Dates. Next, we'll start by using the Calendar Auto function, which takes an argument for the fiscal year end month. We'll be using 12, meaning DAX will return a table from January 2000 to December 2022. We can now commit this table to our model. Navigating to our model view, we see our new dates table containing one column, Date. Currently, there is no relationship defined between our commodities table and our dates table. Let's create a relationship between the two tables by dragging date from the dates table over date in the commodities table. Let's move back to the report view. We can see our dates table in the field pane. Awesome! Now that we have a dates table, we can utilize the built-in date functions in DAX to add additional layers of information to our table. Let's create a new calculated column in our dates table called year. Using the year function from DAX returns a year from the date argument. In this case, we will be using the date column from the dates table. Now we can commit this new column by clicking the check mark. As you can see, this new column has been added to our dates table in the field pane. Let's dive into the topic of quick measures. Quick measures are a feature in DAX that allow you to create complex DAX functions using a drag and drop interface. We can create a new quick measure from the home pane. Doing this allows you to see the range of calculations that you can use quick measures for, including aggregate, filter, and time intelligence functions. Since our primary focus is on working with dates, we'll be using the rolling average function that will return the average of a base value over a certain period of time. For our quick measure, we will look at the average close price over a 3-year period. Quick reminder, our dataset has over 20 years of data, so 3-year periods will help us assess the long-term trends. We'll be using close from our commodities table, which is the close price of the commodity on a given day. We'll then adjust the aggregation to average. Next, we'll use our newly created date column from the dates table for the date. Finally, we'll adjust the period to years and leave the periods before as 1 and periods after as 3. Great! Now, if we select our newly created measure, we can see it's a complex piece of DAX code. This has been used to create the rolling average function. Let's visualize the difference between the average close and the rolling average close. We'll create a line and stacked column chart to compare. We'll use date into our shared axis field. In our columns value, we'll bring in close from the commodities table and change the aggregation from sum to average using the drop-down. Finally, we'll drag our newly created measure, rolling average, as the line value. As you can see from the graph above, the rolling average is a smooth line. This is because rolling averages are useful for long-term trends and are not prone to occasional fluctuations like we see in 2011 and 2012. Our yearly trends are much more volatile versus our rolling average, which shows a general trend moving upwards with a slight dip between 2012 and 2015.
Welcome to this course on data visualization in Power BI. In this course, we will combine a discussion of the psychology of data visualization along with practical tips on using Power BI visuals. My name is Yasin, and I'll be guiding you through this course. Power BI offers 2 methods of showing data to users: dashboards and pixel-perfect reports. Dashboards let us see and act upon critical business or operational metrics, possibly even in real time. By contrast, reports give you more detailed information that won't fit on a dashboard. That's because dashboards are supposed to have a single pane of glass feel, where everything is visible without manipulating the dashboard. However, reports are intended to be printed out, so they can span multiple pages. Dashboards are the norm for Power BI, even when we say the term report. We call pixel-perfect reports paginated reports in Power BI. When designing a dashboard, keep these questions in mind. Dashboards should have specific intended audiences. A dashboard meant for a CEO will look quite different from one meant for an accountant. Think about how they'll use your dashboard. Are they sitting in front of a 4K monitor with a keyboard and mouse? Or are they looking at it on a phone as they move from one meeting to the next? Then, what do you want them to do after looking at your dashboard? The better you understand the viewer's available actions, the better you can tailor your dashboard to give them the timely information they need to act. Finally, are you showing the right measures in the right way? This is an example of a process control chart, and the thing we are measuring has gone out of control. If I show this to a worker actively observing a piece of machinery,
this image alone might spur the person to action. However, if I show it to the CEO, I'm liable to get a blank stare. The dataset we will use throughout the course will be the sales database of a fictitious UK clothing business known as Threads Limited. The company operates across the island through a network of retailers and chain stores. From our dataset, the orders table stores information related to sales orders carried out by Threads Limited. This includes the key financial information related to each order, such as the sales amount and the cost of goods sold, also known as COGS. This variable indicates the direct costs associated with making the clothes the company sells. We also have the returns table that details any orders that were returned after purchase due to errors or faults. There are also several dimension tables that we will be working with. The products table contains information related to the items of clothing that are manufactured by Threads Limited. The retailers table holds all relevant data about the retailers that purchase the items, essentially the company's customers. Our initial audience will be the head of sales of the company, who has a good understanding of the high-level figures related to the company's performance and the products they sell. However, the head of sales does wish to investigate in more detail what type of orders the company is processing and what products are being ordered. The specific output requested will be tailored to her requirements as it is a special project she has asked you to perform. Let's start off by looking at a few Power BI visuals. First, let's create a table. On it, we'll add retailer name, retailer channel, and the total orders made, dragging the table down along the way. Now, we want to add a slicer for the year range. We will use the order date column to find the year orders were placed. Power BI has automatically detected the order date as a date data type. Power BI has also created a date hierarchy for this column, which means we can add the year part of the order date to the field section. The visual can then be resized appropriately. This helps us easily control the different years of operations. Next, we want to check if there is a correlation between the total order quantity and the distance a retailer is from the company's warehouse, based on the regions in the UK where the retailers are located. Let's create a scatter chart, using the average distance from the warehouse as the x-axis, the total order quantity as the y-axis, and the region for the values. It does not look like there is a strong correlation between the variables we have investigated. We might have expected that the greater the distance retailers are from the warehouse, the more items they would order so that transportation costs could be reduced. But this is not the case, which is still an important finding for the company and could help for future strategies. Our final visual is a bubble chart, which is a scatter plot with varying bubble sizes. Here, we would like to see if there are any relationships we can determine between the average price of products, the total quantities ordered, and the total sales amount associated with each product. For example, are cheaper products being ordered in greater quantities or not? On this plot, the total order quantities will be our y-axis. The average price of products are x-axis, and the product name will be the values. We also want to see how the total sales amount relates to the other variables. To do this, we can use the sales amount column and set it as the size. This is an instructive visual precisely because it's so messy. We can see some groups of data points in the visual that probably relate to the product categories, but there is no real correlation that is visible. It is also hard to make out individual points because the chart has too many large bubbles. For this reason, be sure to use bubble charts in places where the size is important. You have relatively few bubbles on the chart, and you can still differentiate individual data points. This has been a look at some of the most common visuals in Power BI. Now it's your turn to take these visuals and tell a story. One of the most important things which dashboard designers overlook is to invoke emotional response from the audience. Let's see how this can be done. Remember this chart from a previous video? What kind of emotional response does it evoke from you? Probably not a strong one. Let's fix that with some context. Suppose this chart shows the bore depth on machinery drilled by a press. We drilled to a tolerance, drilled too far, and we damaged the product, costing a lot of money in the process. You are responsible for managing this piece of machinery, watching for and limiting the cost of failure. With this context in mind, we can see the importance of this chart. Let's look at two specific emotions, happiness and anger. Users are happy because everything looks fine. The sales pipeline is full of great prospects. The machinery is in top order, or we have the best players in the league. Users are angry because something has gone wrong, which is obvious from the dashboard. Happy users don't always need to act, which makes them even happier. Angry users are angry in part because they now need to do something. The worst case scenario is if a person has zero emotional response from a dashboard. That's a sign that the dashboard is not relevant to the user. Since emotions build a sense of engagement, you want to avoid this. You will now be carrying out some data visualization work for the product manager of Threads Limited. The product manager generally identifies what customers want and how the company can develop its products to meet these demands. One of their main responsibilities is the success of the products, so having clear information about current product performance is vital. The product manager at Threads Limited has a large team, so any insights or visuals we will be creating for him will be shared with a wider audience. Therefore, we will have to make sure that they are suitable for a general audience. We will now cover using bar and column charts and formatting visuals. Currently, 3 types of column charts are available in Power BI. Let's start by creating a clustered bar chart. Clustered bar charts are great for showing a variety of data over a single period of time. In this case, we will look at the number of orders by retailer. We can now see a listing of retailers and determine which have placed the most orders. However, we'd like to filter down to see only franchise retailers in 2018. To do that, we'll add a pair of slicers. The first slicer will allow us to narrow down the retailers by channel. After adding the slicer, we will select the desired channel. Then, let's add another slicer and use it to filter by year, including only information from 2018. These visuals are functional, but we can help users understand things better if we format the visuals to include more appropriate titles and axis values. If I select this bar chart and navigate to the Format menu, I have several options available. Let's click on General, drill down into Title, and change it to Total Orders by Retailer and Year. We'll make the X-axis label Total Orders. And let's remove the Y-axis title altogether to save a little bit of space. For the 2 slicers, the set of formatting options available will differ. Let's drill down into the slicer header and change this text to Channel. We'll do the same with the other slicer, changing it to Operating Year. There are a wealth of other options, and it is recommended that you experiment with them to learn more. Formatting options aren't the only way to make it easier to understand the data. We can also navigate to the Analytics menu and add lines to help visibility. It would be good to add a constant line representing the desired number of orders by retailers. Suppose 5 orders are normal for a franchise retailer to make in 1 year. To make it easier to see the line, we'll change the color to black, 20% lighter. Now let's look at stacked charts on a new page. Let's add page level filters to set the year to 2018 and the retailer country to England. Add a 100% stacked bar chart. We'll make the area the legend and add the total orders to the x-axis. This gives us the percentage of orders by area across England in 2018. The South East had the most orders throughout England in 2018. But is this true across all retailer channels? We can add retailer channel to the small multiples field to find out. Small multiples let us break out our chart by some additional fields, making this analysis easy. We can format the small multiples to change the rows, columns, and even grid lines. This packs a lot of information on the screen, but can be very difficult to compare. To make that easier, right-click on the visual and show it as a table. Now we have a tabular view of the data, and we can see that not every channel had its most orders carried out in the southeast of England. Select Back to Report to close the table. The last thing we will do is switch the visual to a stacked bar chart. The 100% stacked chart lets you compare proportions more easily. Switching to a stacked chart lets us compare aggregates, making it easy to see that franchise retailers had much higher orders than the other channel types. These are some things we can do to make visuals easier to understand. In the following exercises, you'll take the reins and build out reports for your audience.
Let's talk about short-term memory and cognitive load. Here is a very simplified version of how humans process signals. Sensory information enters the brain and enters short-term memory. We act on that short-term memory and either drop the information or consolidate it into long-term memory for more permanent storage. When we need that information again, we recall it into short-term memory to use it. George Miller, in 1956, released a study showing that humans can hold somewhere between 5 and 9 pieces of information at a time in short-term memory. Since Miller's paper, further research has noted the importance of chunking short-term memory information, which can help you hold more than 9 individual pieces of info. This matters because of cognitive load. One way to think of cognitive load is how many things on the page can distract me from my task at hand. In this example, we see a somewhat information-dense dashboard with a lot of extra visual noise, things that do not provide timely, relevant information. We also have at least 3 different stories being shown on this dashboard, including total sales amount grouped by quarter, the total cost of goods sold by channel at all times, and gross profit for products in a specific category for a specific year. Here are a few quick wins for reducing cognitive load, and we will return to that dashboard with high cognitive load later on with some specific guidance. Tailor the page to your audience. Understand their needs and design with them in mind. Focus on one story per page. Don't try to jam together multiple stories, as that makes it harder to follow. Pay attention to information-rich visuals. If done right, they can provide a lot of information in a small space. If done wrong, they can confuse the audience. Here are 3 examples of information-rich visuals we will look at: the line and column chart, as well as custom tornado and radar chart visuals. Power BI allows you to include custom visuals in a report. Previously, we saw examples of the tornado and radar chart custom visuals, and here we can see their icons in the Visualizations panel. The ellipsis in the Visualizations panel allows you to import custom visuals from your machine or grab more. One key place to find these custom visuals is Microsoft AppSource. You can connect to AppSource and download free or paid custom visuals if you have a Power BI account. In our upcoming exercises, we will work on projects the company's Chief Commercial Officer, or CCO, assigned to us. This executive level role can have a long list of responsibilities related to marketing, sales, and even product development within a company. Ultimately, their top concern is the company's commercial success, and usually they report to the CEO of an organization. The CCO of Threads Limited is interested in gaining more information related to the company's financial performance. This will include information related to the revenue, the sales amount, COGS, cost of goods sold, and even gross profit. As an executive, the CCO doesn't have ample time to review reports, so we will have to ensure to only include information and visuals that are important in answering the questions the CCO has posed for us. In this demo, we will talk a little bit about cognitive load, line charts, line and column charts, and custom visuals.
Our first goal is to look at historical trends in orders processed by the company over the previous months and years. We'll track that using a line chart, like so. Add order ID to the y-axis field, ensuring the summarization is set to count. Then, add order date in the x-axis field. As it is a date hierarchy, we can choose what we want to show on the visual, so let's only leave year and month there. We can see a range of total monthly orders over time. In the 4-year range of the data, there have only been 2 instances where total monthly orders surpassed 220. It is also possible to see that the monthly orders have dropped to some of their lowest levels in the last few months of the period we have data for. To investigate further and see if this is having an impact elsewhere, let's add a new line and clustered column chart. The x-axis will be the year and month. This is the shared axis for the lines and columns. The line y-axis will be order ID. We can see at this point that we have the same line chart visual. Now we add sales amount. This will show us the total sales amount received by the company every month. We can see that the total sales amount generally tracks the same trend as the total orders. However, there are some periods, such as the start of 2018, where total monthly orders decrease, but the total sales amount stays relatively constant. Further investigation into this period could help Threads Limited improve their more recent total sales amount figures. Let's replace the line chart with our line and column chart, as it gives us additional valuable context. Next up, we'll look at some more details regarding the products, and to reduce cognitive load, we'll do this on another page. On this page, we'll add a filter where the year is 2018. We will now create a radar chart of the product sizes sold by Threads Limited in 2018 and look at a couple of pricing detail measures. Let's add product size to the category field, and then product price and product cost to the y-axis. It makes more sense to see the average of these 2 measures, so let's change the summarization. Nice. Now let's do 2 more things. First, we want to format this so that the colors are not the same. Now I can easily distinguish the average product price versus average product cost. Let's also resize it so that you can see the information more clearly. Now we can see the 5 different sizes sold by the company and the average product price and cost for each one in 2018. Next, we will compare the same measures as before, but for the different product colors sold in 2018. This can be easily done with a tornado chart. The tornado chart requires a group and some values. We already have year as a filter for the entire page, so there is no need to change that. We will then add product color to the group field. For each group, we will compare the same 2 measures as before, average product price and cost. Let's format the 2 columns so that they are both currencies. Perfect. We can see that orange products had the highest average price in 2018 and the highest average cost. Also, even though pink products had the 5th highest average price, they had the 2nd highest average cost. This could be an important insight for the company and could lead to an increase in the price of pink products. Now it's your turn to try this out. Previously, we focused on adding content. Now we will bring the needed balance by removing unnecessary content. There are 3 questions to ask before adding anything to a dashboard. First, does this contribute to the story? Second, is this the right visual element? Finally, is it necessary? Let's talk about each in turn. Think about this clustered dashboard as you answer the following questions. What story am I trying to tell? We have data for a particular product category, total COGS by channel for all years, and total sales amount grouped by quarters. This is at least 3 stories. If I add a new visual, will it align with the story? In this case, the follow-up question is, which story? And that's a bad sign. Keep in mind that the user has ultimate authority. We may think something fits perfectly, but if your users don't see it that way, tailor it to their needs using your expertise. If you're delivering a presentation, you can control the story entirely. But with dashboards, you probably have some filters and slicers, which gives users flexibility. This flexibility limits your control and ability to design explicitly for a dataset. Even so, understand what the user needs and the types of stories they are likely to see. In practice, this means you won't have a lot of static text on a report, because you don't know if that text will make sense given the user's selections. We know that line charts are great for showing trends in data over time. But for most category comparisons, line charts fail because they imply data movement along the x-axis, something few categorical datasets have. For categorical data, we might use a bar chart instead. Choosing the right visual element applies not only to the choice of visual, but also to choices within the visual for emphasis, such as color. Color is what we call a pre-attentive attribute. On this chart, your eyes automatically focus on one particular bar. This focus happens before you can pay attention, making this pre-attentive. Take advantage of this by using neutral colors for bars. Then, you can emphasize something using one color without using words. Think of color as a garnish. A small amount is great, but you don't want to dominate your meal. We don't know where to look if a report has too much going on. Negative space, or places without any information or visual effect, helps us differentiate sections much more easily. Looking at this again, we know that we have multiple stories, so let's focus on one: sales information by products in 2018. For each visual, we can ask 3 questions. Does this contribute to our story? Is this the right visual? And do we need the element? If we follow the prompts for each element, we'll want to remove superfluous images, shapes, and backgrounds, focus on the information related to 2018, and include product-relevant information. Our dashboard is now much less cluttered. The story focuses on sales information for the year 2018. We've retained key information while tightening the story. It's not perfect, but it's much clearer. In the following exercises, we will continue helping our CCO answer certain key business questions and provide more information they can share with the rest of the executives. First, we will look at 2 ways to break down which sizes are selling and to whom. Second, we will look at ways to see if the company is on track to meet certain expectations. For this demo, let's start by looking at 2 types of visuals that show shares of a whole: pie charts and tree maps. We'll focus in on data from 2019, setting a filter where the year is 2019. For our first visual, we will add a pie chart of the total sales amount by product name. There are a lot of different products sold in 2019, so it's hard to see much here with a pie chart. If we change this to a tree map, it's a little easier to see relative share sizes, though we need more space to make it clear. Still, not great though. We can add the total sales amount by enabling data labels on the Format menu. This is an okay use of a tree map, but the best use of one is to work with hierarchical, categorical data. Each of these products belong to a category, so if we add product category to category above the product name, we can shrink the size of the tree map and still get nice fidelity. To navigate in, we have 3 choices. First, we can move down to the next level of the hierarchy, showing us all product names. Second, expand down to the next level of the hierarchy. And third, enable drill mode. Before we go through drill mode, let's add a table. This table will include the product name and the total sales amount. Great, let's continue. Enable drill mode by selecting the single down arrow. When drill mode is active, selecting a level will drill down and expand all elements in that level. If we select jackets, we get just the product names in this category. Note that drill mode is a form of cross-filtering. We can see that the table gets filtered alongside the tree map. Next, let's add a gauge. A gauge needs a value, like the average cost of goods sold. To make the best use of a gauge, you also want a target and a maximum value. Let's create a new target measure of target average COGS equals £350. Let's also create a maximum average COGS measure of £1,000. Putting these measures where they belong, it's clear that the average COGS amount per order in 2019 was above the target set. Let's now perform some conditional formatting. Suppose we want to change the font color on the table to purple for any product with more than £10,000 in total sales amount. For tables, we can navigate to the cell elements, choose which column we will format, enable it for font color, and click on the conditional formatting button. We'll choose Rule from the drop-down list and ensure the field is sales amount. Now we can set for any total sales amount between 0 and 10,000, the font will appear purple. If we sort the sales amount column, we can see anything below £10,000 is shown in purple. Key performance indicators, or KPIs, track performance over time versus expectations. Let's create a new page and see how they work. Next, we'll add a new KPI visual. We'll use the total sales amount as the indicator and the year as the trend axis. Our target sales amount can be created as a new measure and set to £2 million. This will be the target for the visual. We can see that the company did not meet that goal for the last year and was over 10% below it. Let's add another KPI, this time looking at total COGS. Let's create a target for total COGS of £1 million. Drag the relevant measures onto the visual, and it looks bad. But that's not quite right. COGS is an expense for the company, so the lower, the better, but we show that as a bad thing. To fix that, navigate to the Format menu. Select Trend Axis and change the direction to Low is Good. Now we can see that the total COGS for 2021 is on the right side of that measure. We've looked at a lot here. Now it's your turn to try things out.
Hello, my name is Khalid Shukri, and I am pleased to welcome you to this Power BI course. Through these lessons, we will learn the different ways we can use to transform our data to prepare it for analysis. A core concept of good data analysis is that your output will only be as good as the dataset that you use as an input. The saying goes something like, garbage in, garbage out. In order to provide high-quality analysis, you must first make sure your data is of high quality and clean. That way, you will reach a meaningful conclusion about your data and won't waste time working on dirty data. So how do we define clean data? There are some important characteristics of clean data that we must strive to attain before conducting analysis. Namely, we want our data to be free from any missing values, sometimes called nulls. We want our data to have no typos or data entry errors. We should remove duplicate entries from our dataset to prevent skewing statistics. We should focus only on the data that is relevant to us, removing any data which will not help us answer our questions. Outliers should be treated with care, not necessarily removed from our data, as they can be important sources of information. We can apply a floor or a ceiling to the outlier values so that they don't skew our statistics too much. This means that we cap the outliers at a certain value. Columns should have the correct data type to allow us to perform calculations on them. If a numerical column is stored as text, we won't be able to make measures once the data is loaded in Power BI. And finally, column and table names should be short and descriptive, so we don't confuse our report readers and ourselves. Try to make sure your data doesn't look like this table before proceeding to analysis. So how exactly do we clean our data in Power BI? In order to do that, we use a tool called Power Query. This is the data manipulation framework that is present in Power BI, which allows us to connect to or load our data, as well as transform it according to our needs. We then apply a series of transformations to our data, one after the other, so we can fix errors and clean it up. This sequence is shown on the right of the Power Query interface under Applied Steps. You can consider this to be a recipe for how we're transforming our data, and this recipe is saved in your query, which will ultimately load your data for analysis once we close the Power Query editor and apply those steps. There are 5 different data types that are native to Power Query: numbers, date-time, text, logical data, and binary data, which is encoded in base 64 and most often used to store images. We should always make sure to select the correct data type for each column in our dataset. Power BI will also usually automatically detect the data type of each column and set it for you. Transforming our data structure means we won't change the data stored in our tables, only how it is organized. An example of this is promoting headers, which means to make the first row of data into column headers. This can be very useful with Excel files. We can also change the order and sort our columns, as well as remove any redundant columns or rows from our data. Finally, we can rename our columns to be more descriptive. In the first demo of this course, we will introduce you to Power Query and how to do some basic data transformations. Firstly, to access the Power Query editor, we navigate to the Transform Data option in the Home ribbon of Power BI Desktop. There are many features in Power Query that help us prepare our data by transforming it to suit our needs. None of them really work unless we have some data first, so let's import some. When we click on New Source, we will be greeted with all the various data connectors that Power BI has. This library of sources is ever-growing, and you can get some custom connectors from the Power BI Marketplace if you need to connect to a data source that isn't listed here. We're going to connect to a web data source, so let's select the web connector and enter the URL of the website that hosts our dataset. Since this content is freely available for anyone with an internet connection, we don't need to enter any special authentication details. We can just proceed with an anonymous connection. Many data sources will be configured to only allow connections from users with the right access privileges. However, this is outside the scope of this course. If you're connecting to a file on your computer, you won't need to enter any authentication details either. Power Query has successfully connected to the website, and we can see that it has recognized some tables that we can choose to import. We can even see the web view for how the website looks on a browser. We'll select the Best States to Retire table and load it in. To the left in our Power Query window, we can see the query has been loaded in successfully. And on the right, we can see that some applied steps have been automatically generated and applied for us, namely promoting headers and auto-detecting the column types. You can click on any of these steps to preview the data as it was right after the transformation was applied. This can be a really useful feature for understanding the effect of your applied transformations. Since this table is well formatted, we don't expect to see any errors in the column names. But sometimes when loading data, especially from CSV and Excel files, you'll get the column headers in the first row of your dataset, like this. To make the first row into your column headers, you can use the Promote First Row transformation. You can also do the opposite by using the Demote Column Headers transformation. This isn't very wise to do, but let's say I wanted to get rid of the first row, which has our old column names. I'll click on Remove Top Rows and enter 1 into the dialog box. Now that we got rid of the first row, we need to rename our columns so that they are more descriptive. Renaming a column is as easy as double-clicking the column name. Of course, this isn't very efficient, so if I wanted to go back on the transformations I applied, I can click on the X next to each step. Or I can go to the demoted header step, right-click, then press on Delete until End. Now we're back to where we started. If we want, we can reposition columns simply by dragging and dropping them in our desired order. We can also sort the data using a column by clicking on the arrow in the top right of the column name. Let's sort the states by the crime rank to find out which state is the safest. After sorting, we can see that New Hampshire is the safest state. It's now up to you to apply these transformations to prepare the AdventureWorks dataset for analysis. In this video, we will learn a useful feature of Power Query that can help you quickly summarize key characteristics of your dataset. We'll use this feature to help us identify and fix common errors that might appear in our data. Power Query, as we've mentioned previously, is a data preparation tool that helps us transform our data into a state that is more suitable for analysis. To do this, we should have a way of quickly investigating our dataset to allow us to diagnose what transformations are needed. This is where the data preview features of Power Query come in. To access the data preview features, you simply enable them in the View ribbon of Power Query. There are three types of data previews: column distribution, column quality, and column profile. We will learn the exact nature of these features as well as when to use them in the following slides. An important thing to note when working with large datasets is that by default, data previews will only analyze the data in the first 1,000 rows of your dataset. However, you can change that option by clicking on the column profiling based on the top 1,000 rows box present at the bottom left of the Power Query editor. The main reason to use data preview features is to help you find errors and inconsistencies in your dataset. As you apply your transformations step by step, you can also see how the characteristics of your dataset change. So it's also a great way to see if the transformation you applied had the desired effect. Finally, they are a powerful tool to quickly summarize the data in your columns and help you take decisions about what transformation to apply next. The various data preview features are all unique in their own way, so let's see what they are used for. Let's start with column distribution. This allows us to preview the distributions of our columns by displaying a small histogram under each column name. This feature is particularly useful for when you're checking a column for duplicate values. It also shows us the count of unique and distinct values in the column to see how many duplicates, if any, exist. The next feature is called column quality. When you need to check if your data contains any missing values or error values, this is the feature to use. It will calculate the percentage for each of these and show them underneath all column names. Finally, we have the column profile feature, which combines aspects from both previous features. The key difference is that column profiling only works for one column at a time. This enables it to display much more detailed statistics, such as average, minimum, maximum, and standard deviation. You can also find out the distribution and number of unique and distinct values for that column. This feature only works when you select a single column. Since data previews are most often used when you are looking for errors in your dataset, they also come with quick access to some of the most common transformations that you will use to deal with those errors. To view those transformations, simply hover over the output of the relevant data preview feature you're using, and a small tooltip will appear. There, you will find a suggested transformation marked with the light bulb icon. You can also click on the three dots to expand a menu containing additional useful transformations. In this demo, we will learn how to use Power Query data preview features to help us diagnose and fix some common errors that appear in data. The dataset we are working with today is a sample of 99 movie titles from the popular IMDb movie rating database. We have 13 columns of various data types in this dataset, but not all of these columns are going to be useful for analysis in their current state. We can use the data preview features to inform us about the state of our columns and help us decide which columns need fixing. Let's activate the column distribution feature first by going to the View ribbon. This is a handy feature for summarizing the contents of a column, particularly how many unique and how many distinct values are in that column. The first thing we notice here is that the language column has only one distinct value and 0 unique values, meaning that all of the movies in this sample are in English. Since it doesn't add much information, we can remove this column, as long as we make sure to inform our report users that this dataset contains only English movies. Second, we can observe that the color column has 4 distinct and 2 unique values. We can clearly see that there are some missing data points in this column, so we should investigate this a little further. Let's enable the column quality feature. We can see there are 11 missing data points in this column. This is usually a problem, but you can also notice that almost all of the non-empty observations fall under one value. This means there's not a lot we can learn from this column. Once again, we can remove the column and mention it to our audience that we are only analyzing color movies. We can also use the column distribution feature to detect whether there are duplicate records in our dataset. It is expected that the number of distinct director names is more than the number of unique director names, meaning there are some directors that worked on multiple different movies. However, the movie titles should all consist of unique records, so that every movie is represented exactly once in this sample. Since this is not the case, we should remove the duplicates from the movie title column. Now our dataset has no repeated movie titles, leaving us with 91 unique movies. Next, we'll dig a little deeper into specific columns to find and fix some other errors. Let's enable Column Profile. We'll check on the duration column. We can see that the minimum and maximum are quite extreme. There's a movie that's almost 11 hours long, as well as a movie that somehow has a duration of -50 minutes. So let's add a filter to our column to remove these extreme values. I will choose to exclude movies that are shorter than 60 minutes and longer than 4 hours. Now our column statistics look much more realistic. Finally, let's check the title year column. We can clearly see that there are some values that are incorrect, as movies weren't invented until 1895. Here, we can make use of the value distribution part of the column profile and replace these values by right-clicking the bars. Then, it's simply a matter of replacing it with the correct value. Although keep in mind, it is always better to do replacements in the source file rather than in Power Query. This is because if multiple rows have the same value, they'll all be replaced with the value you specify, which will sometimes not be your intent. We've now cleaned up the title year column. It's now your turn to apply the data preview features to help transform your data in Power Query.
Hi there, my name is Maarten van den Broek and I'll be your guide for this part of the course. This chapter is all about transforming the data in your columns, whether it is numerical or text data. First, we'll focus on text data. You will often need to clean the text columns in your data before analysis, as they are prone to data entry errors as well as inconsistencies. Firstly, you should make sure your text columns don't have any obvious typos or incorrect values in them. This can be a little time-consuming to fix in Power Query, so it is better that you fix these errors in the source file if possible. Next, your data should be consistently formatted, meaning that you should not represent the same data point in more than one way, such as having the country column in your dataset have both USA as well as United States in it, since these are both referring to the same country. Likewise, make sure that you are using the same kind of capitalization for all the data points. This will prevent confusion and make the overall experience for you and your report users better. You should also remove all blank space that appears before and after your data, which sometimes appears when loading data from certain sources. The same can be said for punctuation and control characters, which are particularly common when loading data from older data sources and from the web. Finally, a general paradigm to follow is that each column should only represent one piece of information, so you might need to split or combine columns in your dataset to achieve this. Luckily for us, Power Query has many features dedicated to efficiently cleaning text columns, saving us a great deal of time and effort. These features can be found in the Transform ribbon in the Text section. Clicking on Format gives you different options for capitalization, as well as access to two of the most useful transformations when it comes to text data: Trim and Clean. These two transformations should generally be applied to every single text column in your dataset, since they can only positively affect your data. Trim will get rid of all trailing and leading whitespace, extra blank space before and after your data. If there is no trailing or leading whitespace, the data is left as is. Clean, on the other hand, will remove all control characters such as new lines or carriage returns from your data. Although this is less common than whitespace, it can still happen and affects how your data appears when it is loaded into Power BI. An important concept that is particularly relevant to text columns is one related to the specificity of data in your columns. To help us reach the optimal structure for analysis, we are sometimes required to split or merge columns in our dataset. When your data has columns which contain too many pieces of distinct information, it can become hard to analyze and make use of those columns. Therefore, it is almost always better to split that column into two or more columns that each contain a distinct piece of information. A good example of this is splitting an address field into building, street, city, country columns. Sometimes two or more columns in your dataset are more useful when they are combined. This is not a general rule, but will depend more on your analysis needs. A good example is combining first name and last name into a single name column. Let's explore some of the powerful features that Power Query has for manipulating text data. We're going to be working with the AdventureWorks dataset, looking at the customer table. There are 7 columns in this dataset, 5 of which are text columns. First things first, let's enable our column profile feature and column distribution feature so that we can see if there is anything sneaky going on in our dataset. It looks like there are unique customer names and customer IDs, so that's good news. If we take a look at the country region column, there seem to be 3 unique values in the top 1000 rows of the dataset. Let's enable profiling on the entire dataset so that we're able to get a more holistic view. Now there are 11 distinct country regions in the whole dataset. That's strange. We're pretty sure that there should be only 6 different countries. Let's investigate this further. We'll use the column profile feature here. Aha! There are several columns where the same country seems to appear as a separate record. I'm going to filter our column to only have these 4 values to see if I can identify why this is happening. I'll also remove duplicates so that we only get 4 records to compare between. Though they look exactly the same in the table, Power Query sees them as different values, otherwise they would have been removed in the Remove Duplicates tab. We can find out if there is any trailing or leading whitespace or other control characters by counting the number of characters, including whitespace, in each record. First, let's duplicate the column, then head to Extract Length. We can see that the records have different lengths. The correct character length for United States should be 13, 12 letters and 1 space. So the culprit here must be trailing and leading whitespace as well as new line characters. Luckily for us, Power Query has 2 transformations designed to remove these 2 from our text columns, Trim and Clean. Let's apply them to the country column. Now our data is in much better shape, with trailing and leading whitespace removed. Let's remove the filter and remove duplicate steps to see the profile of our column after the changes. Perfect. Let's move to the State Province column. If we scroll through the value distribution, we can see that there are 2 different versions of New South Wales because one of them has a different capitalization. We'll use the Capitalize First Word transformation to make all data in this column have the same capitalization. We can see that our transformation was successful by comparing the number of records before and after the transformation. Lastly, let's change the customer column here to have the first name followed by the last name instead of how it is now. To do this, we'll use split column with comma as a delimiter. Now that we have split the columns, we can merge them back in the right order by selecting the second column first, then holding Ctrl and selecting the first column. Then click on the Merge Column transformation, selecting space as a delimiter. Perfect. Our manager is used to seeing the customer suffix attached to customer names to identify them as a customer, just in case there are any employees that have the same name as a customer. We can do this with the Add Suffix feature in Power Query. Great! Now you're ready to clean up and transform some text data yourself. This time, you'll work on the resellers table. Transforming numerical data is a crucial skill to learn for data analysis. We will learn how to use Power Query's features to fix errors as well as improve our numerical columns to produce higher quality analysis. Earlier in 2016, a Harvard Business Review article cited an estimate from IBM that bad data costs the US around $3.1 trillion a year. That is a staggeringly large number, representing around 1/6 of the United States GDP at the time. The article went to explain that stale and unverified data was being used to make huge economic decisions, which ended up backfiring and caused companies to take dramatic measures to recover those losses. A good rule of thumb to follow is the 1-10-100 rule. It costs a data analyst $1 to verify that a single row of data is valid. It costs $10 for that data analyst to clean that row if any missing or incorrect data is found. Finally, it costs $100 if you leave the data as is and do nothing. Imagine how many rows of data a single company has, and you can imagine how that 3.1 trillion figure is not so unrealistic. Most of your analysis will depend on the contents of your numerical data columns, and basing your results on unclean numbers could lead to a catastrophe. Ideally, you want your numerical columns to be completely free from missing values and errors so that measures we build using DAX will function correctly. Outliers will also affect your analysis, but they will require more advanced tools, which we will learn later. You can use a variety of mathematical transformations on your numerical columns if you had a good reason to apply them. The most useful of these transformations will likely be the absolute value transformation, which gets rid of all negative values in a column. Applying logarithmic transformations to a column is a way to translate an exponential relationship into a linear one. This is an advanced transformation that will generally only be applied if you have a good statistical or mathematical basis for using it. Sometimes you will want to multiply by or add a certain value to all your observations. This can also be accomplished with Power Query's numerical transformations. As a final note, you can save memory and make your columns more readable by rounding your data in Power Query to reduce the amount of decimal places. This is especially recommended if you have many rows in your dataset. Date and time columns are special types of numerical columns, as the standard numerical transformations cannot be applied on them. However, there are a series of transformations dedicated especially to them and will come in handy when you are preparing a date dimension to analyze your dataset. You can extract specific properties of a date column like the year and month, as well as derive properties such as the start or end of a particular year. This can be very useful for your analysis if you need to calculate averages based on how many days have elapsed in the year. You can even extract the age from a date column, which is typically applied when you have the birth date of employees listed in your dataset and you need to figure out how old they are. We encourage you to experiment with the options available to you in Power Query when it comes to date columns, as they are quite extensive and varied. Now let's explore some of the numerical transformations in Power Query. We will be working with stock price data of the S&P 500 index. The S&P 500 is a collection of the 500 largest public companies in the United States. All the columns in this dataset are considered numerical columns, including the date column on the far left. This dataset contains the adjusted closing price for every day from the 22nd of February 2021 to the 18th of February 2022. We can verify this with the column profile feature. You can see the minimum and maximum correspond to the dates I mentioned previously. There are only 253 rows in our data, but this is to be expected since the stock market only trades on weekdays and non-holidays. The volume column contains the daily traded volume in units of stock. However, it can be a little hard to read. We can make it easier by dividing the column by 1 million and then rename the column to specify that the units are millions of units of stock. We accomplish this by going to the standard transformations in the transform ribbon and click on divide. The column is much more readable now thanks to this transformation. The next column we can transform is the deviation to mean column. This column contains the difference between each day's closing price and the average closing price for the whole year. We can use it to calculate the variance of the S&P 500, first by squaring the column and then dividing by the number of samples minus 1. To square the column, we go to the scientific transformations, then we select power, then square. In order to divide by the number of samples minus 1, we select the divide transformation and input 252. Now we're almost at the sample variance. All that is left is to sum the column, which we can do by using the sum transformation under the statistics icon. The transformations under the statistics icon will summarize your entire dataset into just one number, which you won't be able to build measures with if you load into Power BI. We use them mainly for intermediate analysis in Power Query to understand our dataset more. If we take the square root of this number, we'll get the standard deviation of the S&P 500 for the last year, which is a good measure for the average volatility of the US stock market. We can also confirm that this result is equivalent to the statistic in the column profile feature. Let's remove the last two steps here, calculated sum and calculated square root, so we can work with the whole dataset again. When it comes to date columns, there are special transformations that can be applied. Let's say we want to see which days of the week are trading days in the US stock market. We can use the name of day transformation located under the date icon in the transform ribbon. Note that this transformation will replace your column with text data, so it is generally best practice to duplicate your date column first, then apply the transformation on the duplicated column to preserve the original dates. We can also do the same for the month names. This shows us that the month with the most trading days is March, while both Wednesdays and Tuesdays are tied for most trading days. There are a variety of other data transformations you can apply to derive some more insights from your time series data. You will now apply these to clean and transform AdventureWorks sales data. Welcome! My name is Maarten, and I'll be one of your instructors in this course on modeling data in Power BI. So, what is a data model? In short, a data model is a conceptual view of data elements. Typically, this is done in the form of a diagram. Data models include tables, columns, and relationships between tables. They can also include information on data types and keys. Data modeling is the process of creating a data model. It's a critical part of Power BI development. Incoming data usually needs some cleanup and often substantial alterations to the data to find the right insights. This includes changing columns to join together disparate tables, removing non-data rows, or comprehensive changes like pivoting tables. As a result, data modeling techniques can shrink down the amount of disk space needed to store and process data, which improves speed. Finally, data modeling makes the model easier for business users to interpret. Data modeling in Power BI is mainly handled by Power Query, the query editor for Power BI and other Microsoft products like Excel. Its main purpose is to manage the queries which drive dashboards and reports, but also to assist with data modeling. Power Query directly changes the data, such as removing columns. You define your base changes in Power Query and perform fine-tuning steps in Power BI. Let's overview some key data modeling steps you can do in Power Query and Power BI. On a column and row level, there are several options, such as removing specific columns, using the first row as the header, breaking out the lengthy column into multiple independent columns, or summarizing data in a table and grouping it by another column. In Power Query and Power BI, columns can be assigned to data types. The motivation is to constrain your data, ensuring that values match expectations. This can also optimize storage. The numeric value 1 million fits in 4 bytes, but would take 9 bytes as a string. Some functionality is limited to specific types. For example, date arithmetic is only possible on date and time columns. Power Query usually correctly infers the data types of columns and does so using the first few hundred rows. We could also specify decimal places in Power Query. This actually changes the loaded data, so it isn't just a formatting choice. This is useful when there are strict rounding rules. However, typically we want to round after performing all calculations, so rounding in Power Query is uncommon. Formatting within Power BI itself changes the data's appearance, but doesn't affect the stored data. Thus, rounding happens after any calculations. Therefore, we usually prefer rounding here than in Power Query. You now know a few key ways to alter data in Power BI, but these aren't the only ones. You'll discover more during the upcoming videos and exercises about string operations and other column modifications. The dataset we'll be using comes from the United States Census Bureau and summarizes survey data asked of manufacturing firms in 2018 and 2019. It contains a variety of measures around payroll and numbers of employees for several industries according to the North American Industry Classification System, or NAICS. In later exercises, we'll extend this dataset with geography, time, and other dimension tables. Welcome to the first demo. This course will focus on how to model your data in Power BI. Throughout the demos, you'll explore a toolbox of various techniques from which you can choose the right tools to model your data. Let's start with loading the NAICS manufacturing dataset. Select Get Data and then choose Text CSV. This CSV contains several metrics of manufacturers per state per year. Selecting Transform Data brings you into Power Query. Here, you can see that there are two distinct rows on the top. One is a header with short names, one is a header that has descriptive labels. I want to keep this second row for my headers. To remove the first row, select Remove Rows and then Remove Top Rows. You're asked how many rows you want to remove, so enter 1 in this case. Now you can take this new first row and use it as the headers. To do that, simply choose Use First Row as headers. Note that this changed data types automatically. Industry group, for example, is now considered an integer. If you need to change that back to text, you click the data types icon and select text from the list of data types. You're asked whether you want to replace the current data type conversion or if you want to add a new conversion step. Replacing is the default option, since it minimizes the amount of data type conversion steps. Note that there is no default undo action in Power Query. If you want to undo a certain data transformation step at any point, you can do so by clicking the X mark next to a step in the list on the right. Now suppose that your users are used to seeing the meaning of NAICS in all lowercase. You can change this in two ways, by right-clicking the column, selecting Transform, or by going to the Transform menu at the top and select Format. Either way allows you to transform this column into lowercase. With text transforms, you can also, for example, add a prefix to the industry group. This can only be done in the Transform menu. Choose Format and then Add Prefix. Doing this allows you to put in some hard-coded value before each value in the industry group. In this example, you can see code : followed by the original number. You can also perform some arithmetics on your numerical values. Open the right-click menu or select Scientific in the Transform menu to see the different options. Since there are quite a few orders of magnitude between values, you could choose to transform your data using the natural logarithm, for example. Double-click the header to change the name of the column accordingly. Note that we also could round the numbers here in Power Query, but this would actually remove the number of decimals during the data load, rather than hiding them. To apply all your changes and return to Power BI, click Home and then Close and Apply. This will load your data and perform all the steps we just defined. Okay, let's look at some operations you could perform in Power BI. Go to the Data view and select a column to reveal the Column Tools menu. In here, you have different options that only alter the visual representation of the data, like changing the formatting, currency, rounding, or data category. Recall that subsector was a numeric column, but it doesn't make sense to sum these categories. You can change the summarization here to Don't Summarize, so Power BI will inform more appropriate visualizations. It's also convenient to let Power BI know which data category a certain column belongs to, especially in the case of geographic data. For example, under Data category, you can select State or Province here, which will allow Power BI to draw maps correctly. You can also change the way a column is sorted by clicking the drop-down menu. You can even sort this column by another column and sort geographic area name by the geographic ID, for example. This will help creating an appropriate visualization when creating reports, with ordering that makes sense to the end user. Lastly, let's hide a column that has no use for the end user, for example this geo footnote, which seems to be always null. Right-click the column name and select Hide in Report View. Your data is now properly cleaned and loaded, ready for you to start creating visualizations. In this second lesson, you'll learn about database normalization and table operations. Database normalization is a set of rules and processes for data modeling. You could say it's similar to organizing or designing a database. Normalization has a few key goals. First, we want to remove redundant data. That is, when the same information is stored in multiple places. Reducing redundancy can shrink down file sizes and avoids data inconsistency. The final goal is to build out a design which reflects the real world as it is, including how business entities interrelate. As a result, the data is separated over several tables and are connected through relationships, a link from one table to another. Relationships are defined in Power BI. Power Query includes several data shaping operations to get closer to a normalized data model. We'll cover 4 techniques for shaping data: splitting columns, extracting values from columns, merging together queries, and appending queries to one another. Note that all of these are always performed in Power Query. These are the most common practices, but not the only ones possible. Column splitting breaks one column out into multiple columns based on split criteria. It could be after a delimiter, such as a comma or tilde. For serial numbers, we might split after a number of characters, for instance, the first 5 characters representing the brand and the next 3 the product. In the example on the slide, you notice 3A got split into 3 and A. Column extraction takes columns from one table and breaks them out into multiple tables. When extracting a column, we can define keys for the new tables. A key is a column or set of columns which make a particular row unique in a table. On the original table, we retain that key column so we can create a relationship between the tables. In Power BI, you can define these relationships in the model view. With column extraction, we retain just the distinct values of these breakout tables, which shrinks the total data model size and reduces redundancy. You can append a query to combine the contents of 2 or more tables into a single table. It matches rows based on the column names, so watch out for differing headers. It's equivalent to a union all statement in SQL. Query merging is the last option of how you can shape data in Power BI. There are different ways to join tables together using keys, and it is very similar to joining tables in SQL. Don't worry if you're not that familiar with this. It's covered in detail in other DataCamp courses, but it's good to know this option exists. Let's have a look at some table shaping operations in Power BI. This time, we only have our datasets split up by year and need to append them using Power Query. We'll start with the one from 1978. Selecting Transform Data brings us to Power Query. You can see that the first row is superfluous again, and after deleting it, we can promote the new first row as the head is. To append the second table, select New Source and then Text CSV. This table comes from the year 1979. Select OK, since you're already in Power Query. I need to perform the same operations. Remove the top row and promote the new top row as head is. Now that I've done this, I have 2 datasets that are actually equivalent. To create a new table with the 1978 and 1979 tables appended, you can select Append Queries in the Combine section, and then choose between Append Queries or Append Queries as New. The former will replace the current table with the appended one. The latter creates a new table where the 2 tables are merged together. The new table, called Append 1, now contains data from 2 tables, but you could append as many tables as you want. Let's rename Append 1 to 1978-1979 for clarity. For demonstrating purposes, let's break out establishment age code into its own table. To do that, you can copy this 1978-1979 table by right-clicking and selecting Duplicate. For this new duplicated table, I'll use the acronym EAC and remove all columns but establishment age code and its meaning. This table now contains a lot of duplicates, which you can remove by right-clicking and selecting Remove Duplicates. As a result, the EAC table is now a reference or lookup table. We could remove the meaning of establishment age code in our appended table and use this column as the key to the EAC table. The last thing that I want to demonstrate is how to extract values from a column. There are different options to play with, including ways to extract data based on the number of characters, their position, or a specified delimiter. Suppose we just want to keep the last 2 characters from the ID column. In the Transform menu, under the Extract option, I'm going to choose Last Characters. Just keep the final 2 characters and we're good to go. To apply all this and return to Power BI, just click Close and Apply in the Home menu.
Welcome back. I'm Sarah and I will be your instructor for this next chapter. Earlier, you learned that data models provide a conceptual representation of data elements and the relationships between them. There are many approaches to data modeling. We'll focus on one, the dimensional model. The Kimball model, otherwise known as the dimensional model, is one of the most popular approaches to data modeling. There are 2 key concepts in the Kimball model: facts and dimensions. Facts are the metrics from your business process. Dimensions provide the context surrounding a business process. These combine to form a star schema. The star schema's name comes from the way that facts and dimensions connect. We typically have several dimensions surrounding each fact. In this example, measures related to property sales are stored in the fact table, and the lender, salesperson, date, property, and payment type tables provide more context about each property sale. Huge amounts of data are organized in this way in data warehouses. Power BI is optimized to use star schemas over any other way of loading data, so Power BI is faster and easier to use with a dimensional approach. Let's take a closer look at fact tables first. A fact table typically has two types of columns: facts and keys. Facts are the measures or metrics from your business process. Examples include sales, employee count, or number of website visits. They are generally dates and numbers which we can aggregate in some way. Keys are how we establish relationships between fact tables and dimension tables. We expect fact tables to be tall and narrow. They have lots of rows, so we try to minimize the number of columns and how big those columns are. Here is an example of a fact table: property sales. Each row represents a property that was rented at a specific date. The first 5 columns contain keys or IDs that are used to link to each of the dimension tables. You'll find more information about the lender, date, property, payment type, and salesperson here. The last 2 columns hold the measures. Here we're tracking the rent in dollars and the duration of the rental agreement in months. Next, we'll look at dimension tables, which provide the context around facts. A fact may tell you how much or how often, but dimensions give the rest of the story: who did it, how they did it, where they did it, and so on. Dimensions are shared business concepts, usually in the form of a noun such as person, employee, customer, and vendor. Dimensions contain static or slowly changing data. Think of information like names, dates of birth, and height. Dimension tables are typically short and wide. They don't contain that many rows, but do contain a large amount of context for the facts. Let's take a look at an example. Here you can see the salesperson table. The first column contains the same key as in the fact table and can be used to combine the information from both tables. The table also stores additional attributes about each salesperson in the company. Here's that same star schema from before. In the Kimball model, dimensions are often used in multiple facts. These dimensions surrounding property sales could provide context to a different fact table as well. In a star schema, dimensions do not link to other dimensions. This chapter will continue with the census data about establishments active in the manufacturing sector. In the exercises, you will be creating a fact table that contains measures like number of employees, number of firms, and so on. Additionally, there will be more information about the establishment in the form of dimension tables. These include data on the industry, time, age, and geography of the establishments. Hey there, welcome back. Let's take a look at how we can actually implement a simple star schema in Power BI. In this demo, we'll take a data file and break it out into a fact and a dimension table. We'll also load a separate file as a new dimension. The first thing we'll do is go to the Data menu and then select Text CSV to load a CSV file. I'm going to choose the Establishment Survey dataset. I will select Transform Data to open Power Query. Let's take a look at the data first, before making any changes. As you can see, we have data about the geography of the establishments, both at the country and at the state level. It seems like we also have some information about the establishment size. However, this is just the ID. We don't know what the actual meaning of those values are yet. Lastly, we know the year the data was gathered, and the number of establishments is the measure that will go in our fact table. Let's split this file into a fact table and a geography dimension. I'll start by duplicating the query. This new query will form our dimension table. I'm going to rename it to Geography. We only want to keep the columns that provide more information about the geography. So I'll keep Country ID, Country, State ID, and state. I'll select them by holding the Shift key, and then I can keep only these columns by right-clicking and selecting Remove Other Columns. Now, I want to reduce duplicates to ensure we store the data in the most efficient way. To do that, I'll right-click again and click Remove Duplicates. Now, every row in the geography table is unique. Let's go back to the fact table. Since the geography information is stored in our new dimension, it's not necessary to keep it here as well, except for the ID. This is because we'll need to be able to connect the dimension to the fact. So we'll keep the state ID as a key in the fact table and remove the rest. There you go. Our fact table is done. I'll close and apply the changes made. In the data view, we can see both tables now. The last thing I'm gonna do is add a size dimension. As you can see, we have a size ID in the fact table, but we don't know what the IDs stand for. Let's fix that by loading another file. I'll click Get Data and select the establishment size dataset. As you can see, this file contains the actual meaning of the size ID, which is exactly what we need. I'll go to Power Query again, and I'm going to rename the table to size. As you can see, there are a lot of duplicate values, so let's remove those. That looks better. Let's close and apply and go take a look at the data model. To get a better view of the data model, you can collapse the Properties and Fields panes on the right. There is also a slider to zoom in and out of the data view on the bottom right of Power BI. Here we can see the fact table and the two dimensions. The only thing left to do is to make sure there is a relationship between the fact table and the size dimension. Size is connected to Establishment Survey by the size ID. That's it. Using this star schema, we can start creating reports to get insights about the establishments, sliced by geography and establishment size. Welcome back. Let's continue building on your knowledge from earlier. In this video, we'll take a look at Snowflake schemas, an extension of the star schema. Remember from earlier that a star schema consists of one or more fact tables surrounded by dimension tables. The Snowflake schema is like a star schema, except it allows relationships between dimensions. In the example, you can see that the lender and property dimensions each link to other dimension tables. Note that fact tables remain the same. The biggest difference between the two styles is how they handle hierarchical data. Star dimensions tend to have all levels of a hierarchy in the same table, whereas with Snowflake dimensions, hierarchy levels are explicitly broken out into multiple tables. Here you can see a product dimension table. Imagine that each product has a name. Each product also belongs to a product subcategory, which itself belongs to a product category. In a star schema, all levels of the hierarchy, as well as their attributes, show up on the same product dimension. With a Snowflake schema, each level of the hierarchy becomes its own table, and we join those tables, usually with keys. When it comes to dimensional modeling theory, we strongly prefer star schemas over Snowflake schemas. The key reason is that star schemas are easier for business users to understand. They don't want to worry about the keys or hierarchies. The other benefit is that quite a few business intelligence tools have been optimized for the star schemas. Although dimensional modeling theory leans heavily towards star schemas, we do see Snowflake schemas in some data warehouses. The reason for this is that star schemas duplicate quite a bit of data, which leads to storage costs and can impact performance. Also, star schemas are not ideal for frequently updated data, especially with large dimensions. Suppose you have millions of rows in a dimension containing a column for country. When a country name changes, you may have to update a large number of rows with the new country name. By contrast, with a Snowflake schema, this would be an update of a single row. When it comes to Power BI in particular, it is important to note that both schemas work. If you have a Snowflake schema in an existing warehouse, you could import the data as is, making migrations easier. That said, Power BI does prefer star schemas for the same reason as dimensional modeling theory, because it's easier for users to understand. Furthermore, there are some optimizations in Power BI which make performance much less of a concern. Power BI has a built-in performance analyzer. When enabled, it keeps track of at least 3 key measures on each visual. The first is how long it took to read the data from its internal database and then perform any DAX operations on the data. The second component is figuring out how long it took the visual to render. Finally, a third measure captures everything else, which is typically waiting times on other operations, including waiting for cross-filtering operations to complete. There are a number of ways you can improve performance. If the DAX query takes a long time to complete, you could tune your DAX operations or improve your data loading performance. This might include improving your data model. If the big problem is in visual display, use less complicated visuals and show less information on the screen. Power BI needs to render each data point, so plotting tens of thousands of points may take a while. If the other value is the cause of your slowness, you might want to reduce the number of visuals on the page. In this demo, we'll see how to create a Snowflake schema and learn how to use a performance analyzer. Here in the model view, you can see the star schema I created earlier. If we take a closer look at the geography dimension, we can see that it is made up of hierarchical data. Country first, then state. One of the main differences between star and Snowflake schemas is how they handle hierarchical data. Since in a Snowflake schema dimensions can be connected to other dimensions, we can split out the state and country information. Let's do exactly that. I'll go into Power Query by clicking Transform Data. I'll duplicate the geography table twice and rename the new tables Country and State. Let's think about how we want to connect to the fact table. The most detailed level of geography is state, and that is also the ID that is present in the fact table. So we'll connect the state table to Establishment Survey. We'll also need to connect the state table to the country table, which means we need to keep the country ID as well. But the actual country value can be removed here. I'll right-click and select Remove. Next, we'll look at the country table. This one should contain only country information, so I'll remove all state data. Let's also remove the duplicate rows. Looks like there is only one country in our data at the moment. Note that if the country value would have to be updated, we only have to do it in one place in this Snowflake schema, whereas it would be a lot more cumbersome to do this in the star schema from before. Let's close and apply and take a look at the data model. Note that I've kept the geography star dimension as well, so we can easily compare performance later on. In a real-life situation, you would use only one of the two approaches. You can see that Power BI has automatically created relationships between the star dimension and the Snowflake dimensions. This is not right. Let's remove them. I'll right-click on the line and select Delete. Let's do the same for the other table. There we go. So these are our Snowflake dimensions. Now I'm going to create a relationship between the fact and state tables. I could drag the column names on top of each other or use the Manage Relationships button here. I'll select New and choose the two tables. You can see that Power BI has recognized state ID as the key, which is correct. Click OK and close. Lastly, you can see that the relationship between state and country is a dotted line, which means it's inactive. Let's quickly change that by going into Properties. There we go. That's our Snowflake schema. And this would be our star schema. I'm going to go into the report view and create two visualizations. First, I'll create a bar chart with the number of establishments by state, using the field from the star dimension. Then, I'll do the same, but use the Snowflake dimension for the state. Let's quickly rename these visuals to Star Schema and Snowflake Schema. Now we can compare the performance. I'll go to View here at the top and click on Performance Analyzer. This pops out the Performance Analyzer pane. I'll start recording and then refresh the visuals. This will show me the time it takes to load the two visuals on the page in milliseconds. If I refresh a couple of times, we can see that one schema isn't consistently faster than the other. With our small dataset, everything loads pretty quickly. But if you're working with thousands or even millions of rows, the star schema should be more efficient. This is because star schemas will only join the fact table with the dimension tables, leading to faster execution times. That's it. Congratulations on reaching the end of this course, and thanks for taking it. Hopefully, you have a much better understanding of data modeling in Power BI. In the first chapter, you learned more about the basic concepts of data modeling. After that, you saw how to load and transform data from multiple sources with Power BI and Power Query. By the end, you also mastered how to merge and append tables. After that, we moved on and studied one of the most popular approaches to data modeling. You learned all about the basic building blocks of the dimensional model: facts, dimensions, and star schemas. After that, we continued with an extension of the star schema, the Snowflake schema.